scalars and vectors in mathematical physics, and in our last class we had discussed how the vectors are treated and what are the formula of writing a vector quantity, how they are written in a bracketed term, and some commutativity, associativity, and some of the mathematical operations of vector quantity. We had seen how vectors are added, subtracted. We haven't seen the multiplication of vectors, and we knew that the division is not possible for vector. It is meaningless. So if you want to divide a vector by another vector, or if you want to multiply, if you want to divide a scalar by a vector, it is meaningless. Means vector quantity cannot be at the denominator of any physical or mathematical operation. It has to be on the top side. So with that we also learned that there are two kinds of vector multiplication. Since there is no division, multiplications are defined in two ways. One is scalar product and the other one is the vector product. And we had learned that scalar product gives the output which is a scalar quantity, and vector product gives the output which is a vector quantity. So this is what we had learned in a class, and as you can see here, we are using a textbook called Mathematical Methods for Physicists, a Concise Introduction by Taicho, and we were learning some of the vector and scalar things. We have learned all these things, direction, cosine, in our previous class, and then we learned the vector addition, multiplication of a vector with a scalar, and some of the formulae like how vectors are added and subtracted. We haven't seen the multiplication of vectors, and that we'll see in this class or probably in the next class. I would strongly suggest each one of you to go through my previous classes so that you will see if there are something that you missed or you don't know probably before these classes, and you should know before knowing how the scalar product works. Then probably you will learn through my previous videos. I would strongly suggest you to go through them. And for now, let's go with the scalar and vector products, where we'll learn how the vector quantities are multiplied. But before that, I had missed one part in our previous discussion, where we are told that we'll discuss how vectors are added geometrically. We had intentionally kept this aside because I told you that we'll have to see it, means how the vectors can be added or subtracted. So today I'll show you how two or more vectors can be added and how we find the resultant vector, its magnitude and direction geometrically. Mathematically we have already seen how they are done, but geometrically we haven't seen. So let's try to do it in a paper and pen. So here we are, and you can see we are in a blank paper here, and let's draw two or more vectors, and then let's see how they can be added or subtracted. So before that, let me put the origin mark so that it will be easier for us to learn. Let us say this is the origin of the geometry, and let me write out vector addition geometrically. So this is our chapter today, and let us say I have a vector which is facing in this direction. It's not towards top but in this direction, and it has certain length. The length of the vector is its magnitude in geometry. Means if it is 3 towards, let us say, north east, so then the direction is northeast and the value is 3. Let us say I have another vector towards this direction. Let me not add other vectors for now. Let us say this one is small one, so its magnitude is less compared to the previous one. Let me name the vectors. This is A vector, this is B vector. So we know that there are two vectors acting at a point, or you can consider it like some two men are standing and there is a box here tied with a string, and one of the strings is being pulled in this direction and the other one is being pulled at this direction. It's not equal and opposite, they are in about 150 degrees apart, and this man who is pulling it up, this one is stronger than this one. So since this person is stronger, it will apply larger force, and hence the magnitude is big. And on the other hand, for this small person, the magnitude is small. So we don't know where the body will move. Let us say we ignore the friction, the gravity, all other parameters here. We just try to understand if these are the total two quantities, those are working on a vector, means, or on a body. One is pulling towards northeast and the other one is towards southeast, then where the body will move. So this is one of the practical application of vector algebra, where you will find out where the resultant will be. So there is a simple method. You start with a vector, start with drawing it on a different place. Let me just show you how. Now let us say I have a different origin here, and I'll start with this vector. So for simplicity, since I'm using computer, I can probably copy that vector and pull it here. And pull it. So you can see this vector. This is equal in length with the vector A here, and the direction is same. Since I have copied it, there is no doubt that direction will be same. And I am just putting one dot at the center, so that I'll know that this is the origin of this new place where I am conducting. This is the new place. This is new place, this was old. So now in this new place I have drawn one vector which is same as A. Now vector algebra says that how to denote a vector. We say that the arrow sign is H, or the head of the vector, and non-arrow sign is the tail of the vector. So what vector algebra says, you draw the first vector and then try to join the second vector in such a way that the head of the first vector becomes the tail of the second vector. like this. The head of the first vector becomes the tail of the second vector. So I have just copied the second vector to this place. Since I copied it, the direction and magnitude is same as this vector, and I have tried to join the tail of this vector to the head of the first vector. So now in this scenario I have a vector here and a b vector here, which are joined at this point. So now if we want to find out the resultant of these two vectors, what we have to do, we have to draw a line from the origin or the starting point of A to the end point of V, and we have to make sure the origin is the tail of the resultant vector and the end of B is the head of the resultant vector. So this is the resultant vector. And this way we know that if we were moving, we were trying to pull, two persons are trying to pull an object, as we had discussed here. Let me rub some of the stuffs so that it will be clearer. Oops. So we knew that if two persons are trying to pull something towards, one person towards this direction and other person towards this direction, the resultant will be somewhere like this. Of course it's a straight line. Oops. It's a straight line somewhere like this. This is the resultant. So by general approach of thinking, we would also have come to the similar result. We knew that this person is pulling it harder compared to this person. This person has a lower strength, and since this is pulling, this person is pulling it strongly, the object will move more towards this person compared to this person. And since both are pulling to one side of the axis, towards the right hand side, the object will definitely move towards the right side. So that is what we have found here in the geometric way of interpretation of vectors. And this is how vector algebra is, and you can probably use it for any number of addition or subtraction or any number of vectors. Let me show you one more. Say I have a vector in this direction, I have a vector in this direction, I have a vector in this direction. Of course the center, the origin is same for all of them. The origin is somewhere here, and I have a vector towards this direction. Now it's difficult to say analytically that where the resultant will be, in which direction. Yeah, looks like it will be in between these two arrow, because this is of highest magnitude and then this is of highest magnitude and these two are smaller. So in order to make things little bit more complicated, let me add a vector like this. Okay, and let me add a vector like this. Now things are a little bit more complicated. We have 5 vectors here, and for simplicity let me make colors of this vector different, so that we will know which vector are we taking for subsequent uses. So I have made all the vectors differently looking. So I have a black one, a red one, a green one, and blue one, and a magenta one. All 5 are at different directions. And now if I want to find out the resultant of these vectors, it's not that difficult. I'll follow the same procedure. I'll take the first one, copy it, paste it somewhere else. I'll make sure that I am not changing its direction or length. I'll just copy and paste it somewhere else. And since I have taken the black one, now I'll take the red one. I'll copy it and paste it. But I'll try to join the tail of this one with the black one. Oops, sorry. I'll try to join this vector something like snap is on, looks like. Let me just go through it. So here's means ideally it should be completely matching, but for here we can leave it like this. We'll have a, I'll try to find out where this snap is and how to remove that. Okay, for now it's okay. And now is the number of the third one, the green one. I'll just copy it, paste it, and try to make sure that again the head of second vector is matching with the tail of third vector. I'll take the fourth one. I'll make sure it's again the same way. And I'll take the fifth one. Oops. Something like this. Yeah, it has to be correctly done. And now I know that I have to draw a line, final line, that starts with the origin, the first place where I started, and it will end at the final point. So this is my resultant curve. And if I see the direction, it is somewhere between this line and this line, which is obvious because this is being cancelled by three vectors here, and this one is cancelled by this and this. So final resultant is somewhere in between this, somewhere like this. We know from the length standard we'll know the magnitude of this resultant force, and of course the direction is like this if we join these quantities correctly. So in my next video I'll come up with some more quantities, like how you want to subtract something, or how if there are multiple vectors acting on a particular point, and if some of the vectors are additive and some are subtractive, how to operate that and how to find out the resultant. For now we learned that how a resultant is drawn geometrically, and this is a great tool, and with this probably you will be able to, if you draw the magnitude correctly, say if you have a magnitude of 3, 4 or 5 or 9 or 10, and you increase the length or decrease the length of a particular vector in certain scaling ratio. Probably you use a graph paper, or in a digital world you use AutoCAD or SolidWorks or anything, and you make the vectors scaled according to the quantities, you will find out the resultant, which is perfectly correct in its magnitude, and the direction will be okay, and you do not need to go to the I cap, j cap, k cap things. Geometrically you can find out the addition or subtraction of vectors. So we'll move now to our next thing. We will discuss the scalar cross product, scalar products, or what we call is the dot product. So as we discussed, there are two multiplications in vector algebra, and the scalar or dot product gives a scalar quantity in output. We'll see how this is done, and for that let's go back to a new page, and let me write scalar product or dot product. This is called scalar product. You know why? This is also called dot product because it is denoted by a dot, not by a cross. So let us say I have two vectors. One is like this and the other one is like that, and I'll change the color of the second one, and if this is A vector and this is B vector, and this angle is theta. I'll try to use a thinner pen so that theta. So we have a vector, a B vector, and a quantity called theta. It's complicated than I thought. So this is A vector, B vector, and theta. Now if you want to do the dot product, you will write as A vector dot B vector. So how you will find out the dot product? There is a formula for dot product. It is equal to magnitude of A, magnitude of B, and cosine of the angle between them, cos theta. So basically you are trying to find out the magnitude of A. I have not discussed how magnitude of A can be found mathematically. Just geometrically I have shown you it is found by the length and cos theta. So theta must be less than 180 degree and greater than 0. If you see it here in the book, it's denoted as A dot B equal to AB cos theta. See, the italic letters means they are scalar, and since all the quantities are scalar, it will be a scalar quantity. And from this it's quite clear that either we write B A cos theta or AB cos theta, it is not going to change, the result will be same. So it's clear that A dot B equal to B dot A, it doesn't change, and hence the scalar product follows commutative rule. And there are certain formula for using same vectors and different vectors that I'll show you in detail in next class, but I'll give you some of the hints here. if I have a vector A like this, and if I try to multiply it by the same vector A vector dot A vector, then our result will be A cos theta. And if the two vectors are same, cos theta is cos 0, because the angle between two identical vector is 0, and we know that cos 0 is 1. So fortunately the term on the right hand side is not 0, but it will become A square. So magnitude of A square times. So if you are multiplying two same vectors, the resultant will be square of that, but it will be a scalar quantity. Now let us say I have two vectors like this who are 90 degree apart. This is A and this is B, and this is 90 degree. Remember, cos 90 is 0, so our this term has some value, this term has some value, but this will be 0. So our A dot B in this case will be will be 0. So if you are multiplying two vectors which are 90 degree apart from each other in scalar product, the output will be 0. If you are making dot products of two same identical vectors, the output will be square times. This is all because the cos theta term here. Now I believe you all remember the cos and sin theta values. I have a small trick. If you don't remember, I can show you how they are done. Let me show you. So I'll first write some of the degrees: 0 degree, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120, 135, 150 and 180. This is what we should know. So let us say I am first starting with sin theta. So sin theta values are, I'll write by 4, by 4, by 4, by 4, by 4. Sin is always positive up to 180 degree. So I have divided everything by 4, and now I'll add 0, 1, 2, 3, 4, 3, 2, 1, 0, and then I have to do one more operation, that is taking the square. So you know 0 by 4 is 0, 1 by 2, 1 by square root of 2, square root of 3 by 2, 1 and so on. So if you have some trouble in remembering things, you can probably remember this easy way. And for cosine, same thing applies here, but it starts with 4 by 4, 3 by 4, 2 by 4, 1 by 4, 0, and after 90 it has a minus sign. And it has a minus sign, and there is a square root, same way. As the previous one. So you will be able to calculate the values like cos 0 is 1, cos 30 is root 3 by 2, cos 45 is 1 by root 2, and so on. Cos 90 is 0. And since we are dealing with cos theta in dot product, we have to remember these things in terms of cosine. So cos 90 is 0, that means if two vectors are 90 degree apart, the resultant will be 0. Cos 0 will be 1, so that is why it becomes a square. Cos 180 degree is minus 1, so what will be the result? That you should probably comment in my video. We'll see if two vectors are 180 degree apart. This is a vector, and this is another vector. So how the product will look like? And both are same vector. If this is a vector, this is minus a vector, and how the dot product will work. So if you have any doubts or questions, please write in the comment section. I'll make sure that I am answering as many of them as possible and as quick as possible. And I do believe that I've covered almost all the fundamentals in scalar product as of now. We'll discuss some of the things in terms of I cap, j cap, k cap in our next class, and then probably we'll do some exercise where we'll apply scalar product. Of course, we'll see how scalar product can be described in a physical way before moving to the vector product or the cross product. So if you have any questions or suggestions, please do write on my comment section and I'll reply. For now, thank you, and in our next class we'll discuss what are the implications of this vector.